Welcome to episode 7 of the Arcade Dev. This time we'll create a fixed screen display by adding screen ROM memory. And we'll see how the screen memory is laid out to get our picture. Okay, so you remember from the last episode, we put a character all on the screen, the single same character all across the screen. That's obviously not that useful. So what we want to be able to do is vary the character as the screen is basically plotted. And what we've seen is that the frequency with which the next tile is taken in is 4H. So if we time something and change that character whenever the 4H is triggered, we're going to get across the screen, we're going to get characters in the places that we want to vary that pattern. And so what I thought I'd do right now is explain this diagram on the screen is pretty much the final architecture of the Tank Battalion game. And what we've been dealing with so far is just this part here. So it's the render part. So we've seen obviously that the 2L buffer takes in, we've seen that it takes in a character. So we've used a dip switch before. And then on the last episode we used a ROM. And it takes in a character, and then it plots it through the tile map renderer. There's also a bullet renderer, which we haven't looked at yet, but we will do. And then it goes through the color prom and eventually onto the screen. So what we're going to do in this episode is we're going to implement some kind of screen memory. And eventually it's going to be screen memory that is RAM, so what they call video memory, VRAM. And you can write to that with the CPU. So here we've effectively got a split down the middle here we've got the VRAM, and typically in a game, and this is true of lots of arcade architectures, is the video render engine is looking at the video RAM, and it's plotting what it sees. But at the same time, the CPU is able to write to that video RAM. It's obviously looking at the game ROM and maybe some work RAM, which is work RAM 0, work RAM 1, and then writing to the video RAM for this to then be able to see. Now the interesting timing is the fact that we can't have both writing to the VRAM at the same time. And we'll see when we get into the CPU timing how that's dealt with in the hardware, and we have to deal with that slightly differently in the FPGA. But for now what we're going to do is we're just going to set up a ROM file which is going to be our permanent video area, video buffer, and we're going to have a set specific image that it's going to just plot constantly. And we're going to put the characters in there and see how it turns out. later on in the next episode, or a few episodes to come, we can then change that to video RAM and start using a CPU to write to it. So we'll see how that goes. Okay, so this is the Tank Battalion schematic that we've seen before, and this is the 2L chip that we've seen. So this is where we feed in video data, and then it goes through, and this is the tile map renderer which we've seen. This is the bullet data renderer that we're going to look at in another episode, and then eventually gets spat out onto the screen there. This is the video RAM. So effectively this is being seen by the CPU over here, but also by the video interface there. So they both see that video RAM. But the interesting thing here is these three chips, the 157, they're selector chips. And what they can do is they can split between two inputs. If we just go a bit closer here, we've got input A, input B, and output Y. And we can choose the input to output depending on this pin 1 and pin 15. So we can enable the chip with pin 15, and then we can select with pin 1. So interestingly, what we're doing here is on the input A, we've got it connected to the address bus of the CPU. And on input B, we've got it attached to the timer chips that we had, the 161s, and we've got it attached to these 128V, 64V, 32, 16, 8, and then the 128H, 64, 32, 16, 8H. And what that's going to do is it's going to create a kind of scanning address that will look through a specific set of addresses for the video buffer. And in this case, here it is going to be searching through video RAM, but we're going to make it search through a video ROM because we're going to program a ROM with it instead. So what I've got here is a slightly modified version of these three chips. The inputs to A are still the CPU address lines. Now A11 down to A0 we're not actually going to use for now because we don't have a CPU connected. So although I'm showing them, we're not actually going to use them. And then on the other ones, the let's say the second inputs, we're tying the top two to ground, and then we're going to tie, as per the previous schematic, 128, 64, 32, 16 and 8 V, and then the 128, 64, 32, 16 and 8 H. And the outputs are going to go to address bus 10 down to 0. Now what we're going to do is we're going to attach those addresses to a ROM chip, and this ROM chip is going to be programmed with a predefined screen that we're going to do. And then that screen is going to output the data when we have a selection address. It's going to output the data into our 2L chip. And you remember, as we said, as long as we feed some data to 2L every 4H, if we change that every 4H, we can change what we show on the screen. And we've got a few little other features. We're going to include the 256H enable on these two chips here. We're going to tie that to ground on this chip. And all that's going to do, we're going to see that is going to affect how this timer goes. So we'll have a look at how that counts up in a little bit. Here I'm just going to show how this is creating a different address. So this VA along the top here, is the input to that 11 down to 0 bits. And what it does is it creates a counter that goes from 000 to 00F, and then it counts again from 000 up to 1F. And then after that we come into our H blank, and during the H blank we're going to have our 0 to F again. And that was just a feature of how this counts. And the reason why that is, we'll see later, is it's a clever feature that when we have the H blank, which is at the end of a horizontal line, this is then going to start looking for data about the bullet, which we can disregard for now. All we need to worry about is the fact that we are having a count from 0 up to 01F, and we do that 8 times. And we do that 8 times because for every single row we have 8 pixels on it in a particular square. So this counter is very clever. It counts the same sets of rows 8 times, and increments the V value by 1. So if you remember, if we go down to the sprite chip, the tile chip here, these 4V, 2V and 1V, that was creating a count of 0 to 7. So we take in a particular number for the character we're looking at. This doesn't change while this counts up an extra 8 times. This graphic shows the first line memory from 000 to 01F. That first block is made up of 8 lines as shown, and the 8 lines are created by varying the V counters, and change which part of the character ROM is addressed. For a refresher on that and how it all works, check out the last episode. So the screen memory is laid out. If we're looking at the TV as it's normally placed, it will start top left and it will do a raster scan from top left, right, and then down, and it goes from memory 000 up to 01F, and then every line, so that's 32 squares, and it will go down until it reaches 37F. And in actual fact, the chip that we are going to use for this will go to 3FF, which will be 400 hex, effectively, in terms of the space. So every single square of these is triggered on a 4H timer. So as long as we change our information every 4H, we can program in to a chip at a certain address what we want to put in these locations. Now the actual screen has been rotated, so instead of being top left, we've rotated it around, and it starts here on the top right, 00, and it goes downwards to 1F there, and then it fills from right to left. And that's just because we've taken the screen. A lot of these games like Pac-Man or Tank Battalion, Frogger, Pengo, they're all vertical games, and so it's just the screen turned on its side, but the mechanics are still the same. It still plots from left to right and from top to bottom, but in terms of if we want to put something on the screen, we got to bear in mind that it's gonna look in this kind of way, and so we have to train our minds to thinking what we would put in memory to get the correct picture. So what the plan is going to be putting a picture on the screen that has a green border, and it has the message MiSTer Retro Wolf Namco 1980 or 2022, and then a piece of wall. And so we need to take the previous character map that we had, and we replace those letters with the character identifier in that character map, and then we need to place those into the ROM file just at the correct location, and the hardware is going to find that for us and plot it into the renderer. So that's it converted to the memory locations. So all I've done here is we had our previous memory map there, and I've just put in the respective codes for the graphics that we want from the tile set. So next what we need to do is put that into the actual ROM file and program it onto an EEPROM chip. So here's the hex editor, and I've created a file that is 2K long, and 2K is 800 hex or 800 hex. And so from 000 down to 3FF is the size of our area, our screen area. Although the first two lines won't be displayed, and the bottom two lines also won't be displayed. So that's just basically how the hardware is set up, that it's only really going to be looking for data in those in about 40 hex down to 3BF, which is just there. So typically when we look at hex files, we're going to look at them 16 wide, sorry. So if you say bytes per row, 16, that's typically what it looks like. The problem is if we look at it that way, each line is doubled up, so a line would go from there and it gets pushed under, so it's quite difficult for us to see and place characters into this. So a sensible and useful way to do it is to change it bytes per row, go to 32, and if we do that, this is a direct view then of what the screen will look like. Obviously on its side, as I said before, so that would be how it plots it on the TV, but not in the vertical sense. So to have our wall around, we've got our green border, which is the symbol or the character identifier 10. So that's going all the way around there, then goes all the way around there and there and there, and then we've got our MiSTer Retro Wolf, and then we've got the Namco there, we've got 1980 to 2022 piece of wall, and then we've got two sprites there. I think one of those is an eagle and one is a tank, something like that, I can't quite remember. So that's that. So we've got this, and we can save it MiSTer Retro Wolf screen.hex, and then we can write it to our EEPROM file, our EEPROM chip, the 2716, and then place it into our breadboard connected to the 2L chip. So here's the breadboard. What we've got here, instead of the dip switch, you remember before we had a dip switch here, and we were selecting the input to this 2L using 8 switches. Now instead of doing that, what we're doing is we're feeding a data line from this ROM chip. So coming out this data line straight into here and then into the 2L chip. I could have taken away these resistors, but I just left them there. They're not doing any harm. So that's the data from this 2716. The enable pin, enable low, is just tied to ground, so it's always enabled, it's always on, and that's fine for this particular application. And then, as we said before, we've got these selector chips here, the 157s, that are connected to the 161 timers that are creating the kind of lookup table. So it's doing a search from 0 to 3FF, and then that is creating an address lookup to look up in this ROM chip. So just looking back at this schematic, just to remind ourselves that the inputs are there, and then the outputs come out here and are fed straight into that ROM chip, and then that creates a data output that's then every 4H creates a square on the screen. So there we go, we've got the ROM there showing the screen that we created, and it shows that we can just put in characters into the ROM and it's going to get the render, the video display side of the circuit, just showing whatever we want there. Now imagine if that, instead of being ROM, was a RAM buffer, and then we're writing to that RAM buffer. That's obviously how we then get that to change real time on the screen. So that's what we're going to look at in the next hardware episode, how we can do that.